Black holes in the media are portrayed as matter-thirsty objects with infinite hunger. They tear astronauts apart, cause incalculable damage, and facilitate impossible feats of time travel. These often misunderstood objects have been discovered and studied only over the last half-century. Black holes reveal to us the depth and breadth of the known universe and the tremendous success of general relativity, but they do hide their dark sides. As the brightest objects in the universe, quasars and blazars are powered by supermassive black holes accreting material onto accretion disks. Recent black hole mergers, observed by LIGO, reveal just how many black holes are out there. And observations from the Event Horizon Telescope give us our first glimpse at Sagittarius A star, our galaxy's very own supermassive black hole. But physicists are well aware that we have much more to learn about black holes, and to pass that knowledge on to artists and filmmakers who have a passion for science.
In this course, we learn that a black hole forms if we can find a way to squash the mass of an object down into a small volume with a radius less than or equal to the Schwarzschild radius. It's difficult to make a black hole, since as matter is squeezed into smaller volumes, other forces will tend to oppose this motion and push outwards. For instance, in a star, nuclear reactions in the core of the star heat up the star and provide an outward gas pressure that balances gravity. As a result, we have stars that can live long, stable lives for billions of years, potentially providing heat to life on orbiting planets. Black holes can form when very high-mass stars can't provide enough heat from nuclear reactions to provide the gas pressure and keep up hydrostatic equilibrium. The loss of nuclear fuel leads to the implosion of the star that can, in some cases, create a black hole. Another way to create a black hole is to smash two neutron stars together. If the resulting mess of material has a high enough mass, it can collapse into a black hole. I don't know about you, but I'm feeling overwhelmed by all the information I learned from the course. I really want to go back now to the scenes in Star Trek that we discussed at the beginning of the course to compare what we saw then to what we know now. As you probably recall, in the 2009 Star Trek movie reboot, red matter is employed as a quick method of creating a black hole. While there is still no scientific basis for red matter or even the creation of a black hole through current human technologies, the destruction of the planet Vulcan due to a black hole is still a frightening thought. We now know that even if it were possible to create a black hole, say in a particle accelerator like the Large Hadron Collider, the black hole would be tiny. It would be so small that its temperature would be millions of times hotter than the sun, and quantum effects would quickly work on evaporating a black hole through Hawking radiation. If the mass of the red matter black hole were similar to the mass of a proton, then the Hawking radiation would make the black hole unstable, and it would disappear in a tiny fraction of a second after it was formed. This might create a small burst of energy, but not nearly enough to destroy a planet. That's not where the scientific inaccuracies stop either. Let's say that red matter did create a miniature black hole that caused the collapse of the planet's surface. The planet wouldn't vanish as it did in the movie. Instead, the infalling matter would accrete around the black hole, heating up to thousands and millions of degrees. Instead of watching the collapse, you would see instead blinding X-ray radiation, literally blinding if you happen to be close. Although scientists have never observed such low-mass black hole, it's likely that all models applied to accretion disks of larger black holes would scale appropriately. I don't bring up these issues because the scientific inaccuracies make Star Trek a poor movie. Quite the opposite, in fact. Without shortcuts around some of the difficult scientific principles, Star Trek would just be another documentary about black holes. But when scientific principles are applied correctly, like they were in Interstellar, the whole story gains a renewed significance. Where Star Trek lives in the realm of science fiction, we can envision ourselves in a scientifically accurate future like Interstellar portrays.
We can often find shortcuts taken by filmmakers and artists while portraying the astonishing environments around black holes. But the reality of black holes is much stranger than anything that has yet been captured on film. Science fact, as it were, still beats science fiction for this strangeness of black holes. Einstein's insights into the structure of space-time, insights that required a powerful imagination, along with a knack for mathematics, were a giant leap from the Newtonian framework of gravitation. As a result, We know that in our universe, there's a trade-off between how quickly you can travel and how quickly the clocks in your reference frame tick. Even thinking about that is giving me a bit of a brain cramp. Imagining space-time is nothing compared to speculating about the interior of black holes. In both Disney's The Black Hole and Christopher Nolan's Interstellar, characters are portrayed as crossing the event horizon. As astounding as the effects may be, the events portrayed in these movies, taking place within the event horizon of a black hole, is pure speculation. Physicists make use of Penrose diagrams to try and explain the interior of black holes. Modern theories predict that anything that enters into a black hole will have to collide with the singularity, which is likely fatal. We talked about the escape from a black hole as an impossibility, but we also know that the process of Hawking radiation allows the escape of particles from a black hole when pairs of particles and antiparticles are created near the event horizon. So, which is it? Can particles escape from black holes, but not something big like me? As quantum physicists are keen on saying, information cannot be destroyed. So what happens when I drop a memory device into the black hole? Can I read that information out of the Hawking radiation at a later time? Does the black hole somehow encode everything falling into it as the universe's most compact hard drive? Until we can observe black holes in greater detail, we may not be able to learn the answers to these questions. These are the questions that I spend a lot of time pondering, and I hope that I've gotten you thinking about them as well. It has been an honor teaching you.
The idea of a black hole has been around for a long time, and more recently a key component of many science fiction tales. Optical observations of black hole binaries have allowed us to look at the companions to black holes, watching them move in orbit around the binary's common center of mass. Using this information, we have been able to find out more about the types of stars that hang out with black holes. We have been able to learn about how they can transfer material to the black hole and how black holes can get their food. X-ray and radio observations of black hole binaries have given us the opportunity to learn more about what's going on close to the black hole by giving us an insight into accretion processes. These views allow us to test theories about the physics of matter in the presence of extreme gravity. While we are currently unable to visit a black hole ourselves, observations of them have taught us much more about the universe. The closest known black hole to us is V616 Monocerotis. It lives about 3,500 light-years away from us. V616 Mon is a black hole that lives in a binary system with an orange companion star. The black hole weighs in at about 7 solar masses. The furthest known black hole, ULAS J1342 plus 0928, was discovered in 2017. This supermassive black hole has a mass of 800 million solar masses. Its light has taken 13.1 billion years to get to us and was emitted only 690 million years after the Big Bang. The discovery of distant black holes allows us to learn more about the early universe, the formation of the first supermassive black holes, and the formation of galaxies. The smallest known black hole, XTE J1650-500, with a mass that is approximately 5 times the mass of our Sun. This means the event horizon radius is only 15 kilometers. The largest known black hole is S50014 plus 81, an optically violent variable quasar. This black hole's mass is 40 billion solar masses and is also one of the most luminous black holes, emitting radiation equivalent to 10 to the power 14 suns. The faintest black hole is something harder to determine. One contender is Swift J 1357.2 minus 0933, a stellar mass black hole in a binary system located only 4,900 light years away. And it emits light that is only 100 times brighter than the Sun in the X-ray band.
I want to thank you for joining us on this learning expedition. While black holes appear to be mysterious, we have learned that the basic ideas and observations can be described using known scientific principles. Astrophysicists are well aware that a theory of quantum gravity is required to explain quantum phenomena associated with black holes on tiny scales. However, there are plenty more unknown unknowns that we can only just begin pondering about, like the nature of gravitational waves. The observations of gravitational radiation from merging black holes and neutron stars has opened up a new way to learn about black holes. We can't know what will be discovered, but we can guess at some possibilities. I'm hoping we will observe gravitational waves from merging supermassive black holes at the centers of galaxies. Maybe we'll get to see the first evidence for a binary system composed of a neutron star and a black hole, giving off gravitational waves as they merge. It may also be possible to see gravitational waves when stars are tidally disrupted by black holes. I hope that you have gained the tools to understand new discoveries about black holes and to communicate those ideas clearly. Maybe one day I will read about your new discovery. Thank you.